we should be very clear about the notion of acceptance by a Turing machine, because this notion is somewhat different from the notion of acceptance as we were familiar in case of finite state machines. Now, recall what we said about a string being accepted by a Turing machine. So, we said that the configuration, initial configuration was the Turing machine was in the initial state Q0 and scanning the leftmost symbol of the input string, let us say the input string is X. Then we said that if 0 or more steps from this configuration, the Turing machine goes to a configuration alpha p beta, where p is an accepting halting state, all accepting states will by definition will make them halting. So, when we say the machine enters an accepting state, at that time the machine has decided that it is going to accept the string. So, therefore, there is no reason for the Turing machine to operate any further. So, when from the initial configuration it reaches a configuration where the state is an accepting, which is halting state, then we say, if such a thing is possible, then we say that the input X is accepted by the Turing machine M. Said to be accepted by the Turing machine. And we also use the word rejected. A string is rejected by a Turing machine. What does rejection of a string mean? Rejection is a word which is equivalent to the string is not accepted. String is not accepted means that this situation will not come about. Now, you can see that non-acceptance or rejection can happen in two ways, And what are these two ways? One, the machine enters a state which is halting but not accepting. TM enters a non-accepting halting state. That is, after some time on the input, the Turing machine enters a state. From there, no further computation will occur, and that particular state is not an accepting or a final state. In that case, of course, this situation has not happened, and therefore, that input string is not accepted or rejected. However, there is yet another way a string can be not accepted or rejected, and that is Turing machine invokes a non-terminating computation. What do we mean by this? That the Turing machine keeps on working and it never comes to a halting state, and therefore, it has not reached an accepting state, which by definition is halting, and the work of the Turing machine goes on forever. But in that case, this situation would not have occurred. And what is that situation? In 0 or more steps, which is always finite, can be arbitrarily large, in some number of steps the machine reaching a final accepting state. So, in this situation again this will not come about, and therefore, the input is not accepted, or another way of saying that is input is rejected. The point I am making is important, that acceptance of a string is an event, in the sense that the string invokes a computation which finally reaches a state which is accepting and halting, whereas non-acceptance need not be a definite event, in the sense a definite one, this corresponds to non-acceptance by a definite event, that it has reached a state which is a non-accepting but halting state. So, at that time the Turing machine would know that the input string is not accepted. But on the other hand, if this is the case that happens, Turing machine goes on working, so there is not a definite event by which one can say that the Turing machine would know, or you would know if you are just looking at the process of the computation of the Turing machine, that the string is rejected. So, the point is acceptance is a definite event. What is that event? And that event is the Turing machine reaching and accepting halting state. This reaching and accepting halting state is a definite event. So, therefore, acceptance is a definite event, whereas non-acceptance need not be a definite event, and that is the case when the machine invokes a non-terminating computation. Just to illustrate this point, let us take a very trivial example of, let us say, the language it is the all blocks of one strings which have length even. So, this is the language L. There is a very simple Turing machine to accept it or to recognize this language L. And in this case, in this state, if you see a blank, then you halt in a and not accept. So, remember the what input would have been written like this, that there is a block of ones flanked by blanks on both directions, and if you start the Turing machine here, if you just trace, starting from here, it sees the first one, it does not change it, but moves to the right and so on. It sees here this one in this state, and it again does not change this one, but moves to the right, and finally it will be here in this state, and here it is seeing a 1, right. So, what is going to happen? This one, it was here, it has come here, and this one, it is here and going there and so on, and after some time it is going to see blank, right. Now, in the beginning, if there if the string was 0, length 0, then of course it sees blank and it should halt and accept, because that means n is equal to 0. On the other hand, if there is, see, basically a string of length even length drives the machine here, string of length odd will drive the machine finally here. And at this, after moving to the right, if it sees a blank, then it knows the string that it has seen is odd, and therefore it will halt and not accept. And in this case, if it sees the end of the input, which is a blank symbol, it knows that it has seen what it has seen as an even length string, and the input is over, and therefore it should halt and accept. In this trivial example, both acceptance and non-acceptance, they are definite events, right? Because when it accepts, of course, acceptance we said is always a definite event, it halts and accepts. But here, when it is not accepting a string, it is halting but not accepting. Now, suppose what we do here is that here, instead of halt and not accept, we make the machine go into an infinite loop, and that can be something like this. So, what happens after it has seen an even number of odd number of ones, it will be here, will see a blank, and therefore it will go to this state, it will move to the right, and again of course it sees a blank because everything was blank here, it keeps the blank symbol as such, goes to the left, and then it will again see a blank, it again does not change that blank symbol, goes to the right. So, it just goes on in this loop infinitely, on and on and on and on. Now, here what is happening? On a string of length even, the machine will halt in an accepting state. On a string of ones which is of length odd, the machine is going into an infinite loop. What is the language this particular Turing machine recognize or accept? Clearly, the strings which take the machine to the halting and accepting situation here, those are the strings which are in the language accepted by the Turing machine. So, that is same as the one before, whereas here it is doing some non-terminating computation on strings of length odd, but that does not change the situation so far as the strings of even length are concerned. So, my point is, even this machine which is invoking an infinite computation on strings which are not accepted, this particular machine also accepts this same language. So, the two machines, although this is slightly silly way of doing this, but it is perfectly all right to claim that this machine is also a machine which accepts this particular language. So, therefore, as you can see that the non-acceptance or rejection of the strings which are not in the language, in this trivial example, those are strings which are of length odd, and they invoke finally an non-terminating computation, but that is fine. But even then those strings are not accepted, because these strings, these odd length strings, do not come to this situation where the machine goes into a halting and accepting state. So, we have clearly need to understand this particular point. There is one more point I would like to make here, and then go over to generalizations and restrictions of our basic model, and that is the point I am saying is that this is of course a convenient way of representing a Turing machine, but we have said formally a Turing machine is what? Formally a Turing machine is a number of things. Basically, it is a tuple, that is the way you say what something formally is, that a Turing machine is a tuple consists of set of states and tape alphabet, input alphabet, then transition function, then a special symbol blank, this is the symbol which is initially there in most of the tape cells except the part which are occupied by, except those cells which are occupied by the input. And what else do you need to specify a Turing machine? You must say where would the Turing machine start, which state the Turing machine would start in. So, this is the initial state, and we must say also which are the final accepting halting states. So, I will not say again and again accepting final halting states, because we assume always that a final or an accepting state is a halting state. So, let me just simply say these are final states, or also equivalently you call them accepting states. So, I would like to make sure that although informally we describe Turing machines, simple Turing machines using diagrams like this, transition diagrams like this, formally we will represent Turing machines through such a tuple by definitely specifying what the set of states are, what is the tape alphabet, and so on. Remember that this is a finite, all these are finite entities, because this is for a particular Turing machine the set of states is finite and so on. So, let us take this particular example and work out so that we are absolutely clear that the formal way of specifying a Turing machine by means of such tuples and then enumerating each one of them separately, and a diagram like this, they are not you can go from one to another. So, what would you say set of states of this machine is? So, if you say this machine is M, so you can clearly see that we have of course these 4 states, but also there was another state here, which is the halt, which really stood for the final halt or accepting state, in which of course you halt. So, suppose I name this as Q0, this as Q1, this as this state which is the halt and accept as Q2, Q3, Q4. Now, basically we are saying that our the set of states Q will be Q0, Q1, Q2, Q3, Q4, and the tape alphabet consists of, in this example, remember what we had initially was just a block of ones flanked on both sides by blanks. So, and we are not writing anything other than 1 or blank, right. So, this even a blank you write blank, that is okay, and this is it. So, the tape alphabet consists of 1 and blank. Input alphabet, input was a string of ones only, right. So, input alphabet is just 1, consists of the symbol 1, and now delta, right. Delta you have to specify by giving the map which would tell me, given a present state and given the symbol being scanned, what will be the next state, etc., etc. So, we can see delta I can specify by means of a table, the table of quintuples, and given something like this, present state, present symbol, next state, symbol written, and move, direction of move. So, just to be very clear, for the if the present state at Q0, in Q0 if you see a 1, then you move to state Q1, you write, of course, do not change that symbol to anything else. So, you write it as 1 itself and you move to the right. So, this is the arrow which corresponds to, this arrow corresponds to this row of this table. In Q0 you can see a blank. If you see a blank, what do? You go to this halt and accept state, which we are calling it Q2. And and move in which direction? Maybe you just move right, it does not matter, and so on. You can fill up this table. So, only thing, if Q2, since we are taking Q2 as our halt state, that means from here nothing happens. So, there will be no quintuple with Q2 in this column. That means, once we reach Q2, then the Turing machine has nothing to do, and therefore, another way of saying is that it halts. Okay. So, all I am trying to say in this, that the way this was a finite object, this diagram, and this had all the information, corresponds to giving a very formal way of specifying a Turing machine. So, like this arrow which coming from nowhere into the state Q0, it signifies that Q0 is the initial state, which we have to mention here, right. What is the special symbol? That is not really written here. I mean, from this diagram you can't really make out maybe that what is the symbol which is there initially for most of the cells, and that is one limitation of such a diagram, but you can otherwise specify that the symbol blank is what will be there in the most of the cells in the beginning, all the cells except where the input is present. We are kind of assuming that the input alphabet does not itself contain blank without any loss of generality. Now, from here, now that we understand acceptance and non-acceptance of a Turing machine clearly, and also we understand informal definition and formal definition of a Turing machine by means of specifying all these tuples, this particular tuple, and then specifying individually each one of these. See, these are all, each one of this is a finite object, like this delta, which is the transition function, is a finite table. We made the point why it will be a finite table, simply because both set of states and the tape alphabet, these are finite sets, and therefore it cannot have more than cardinality of q multiplied by cardinality of gamma rows here. It cannot have more than so many more rows than cardinality of q multiplied by cardinality of gamma, and therefore this table is also going to be finite. So, Turing machine is a finite object, whether you can represent it by means of a diagram like this or by means of more formally a table and tuple. In any case, the point I am making, and I hope it is absolutely clear, that one particular Turing machine is a finite object. All right. So, now from here we will look at certain generalizations or restrictions of Turing machines, our basic Turing machine model, and argue that neither the generalizations nor certain restrictions make any difference so far as the language recognition capability of Turing machines are concerned. So, just to get back to the motivation, we defined a class of languages called recursively enumerable languages, and we said a language is recursively enumerable, or for short a language is RE, if there is a Turing machine to recognize that language, right. And our Turing machine model was that basic Turing machine model, that it has a tape which is going on to infinity in both directions, and there is a finite control with finite states. The machine can move up and down, changing state, changing symbols in cells, and so on. And we would ultimately like to claim that by means of whatever algorithm that you may think of, you cannot ever recognize a language which is not recursively enumerable. And also we will claim the other way, that if a language is recursively enumerable, then that language decision problem, at least where given a string, whether it is, if it is accepted, we can have an algorithm which will halt and say the string is accepted. So, basically we would like to, as I said right in the beginning in our discussion of Turing machines, that we would like to equate the informal notion of algorithm with notion of Turing machine computability. So, therefore, the question which becomes important is that we are working with, we have defined this particular model, which we may call the basic Turing machine model. So, the question which might arise very naturally is, then look, maybe that if you change this model a little bit without intuitively losing the idea of effectively doing computation, maybe then the class of languages which are recognized by changing the basic model will be different from this class. So, in that case this class will not be robust. In fact, what should we do to convince ourselves that this is a good enough model? We do not need to think of any restrictions or any generalization which are natural enough. So, you may say, or the point we are trying to prove is the robustness of the basic Turing machine model. So, two things we can do to the basic Turing machine model. Either we can add some extra capabilities, or restrict some capabilities. So, what I am saying is, suppose we do this to our basic Turing machine model and then find that whether we add some extra capabilities or whether we restrict some capabilities, some natural things, we do not want to do something very unnatural ones on the basic Turing machine model, then the new machine, the class of machines that we get, do not change the class of languages accepted. In that case, we can claim that this set of or this class of languages defined through our basic Turing machine model is a good class, because changing small things here and there do not make any difference to the class of languages which are or which is recognized. So, first of all, we will try to add a few capabilities to the basic Turing machine model. This is model, and let us see what we get. We are talking about tape, and in our basic Turing machine model, the tape, you may say, has a single track, in the sense the tape consists of an array or just arrangement of linear arrangement of cells, and each cell can have exactly one symbol. But you might have known, you might be knowing about real life tape devices, and there people talk of tracks, that a tape has not just such tapes are not just a linear arrangement of cells which can contain exactly one symbol, but the kind of picture that we will have for a multi-track tape will be something like this. Right? This is 4 tracks, and each track is like this thing, this tape, right. So, you may have a symbol A1, A2, A3, A4. So, basically on the 4 tracks, this is a 4-track tape, and you can have different symbols occurring at different tracks, and then what is your read-write head would do. Suppose instead of a single track Turing machine, we had a 4-track tape Turing machine. Now, you can see it is reasonable that if this is my read-write head, and that is what happens in real life tapes with multiple tracks, simultaneously the read-write head will read all the 4 symbols on the 4 tracks. Is it clear? So, if the tape head is here, it is going to read all these 4 symbols. The machine is in some particular state, and depending on the contents of these 4 cells, it will make its move, and that move will consist of changing into a new state, writing symbols here in these 4 cells, and then moving the head either one step to the left or one step to the right. So, in other words, what we are describing is a multi-track Turing machine. Right? So, we have added an extra capability to our basic Turing machine model. The basic Turing machine model had only a single track in its tape, but in a multi-track Turing machine, we have several tracks. In this particular example picture, the tape has 4 tracks. We are now considering, therefore, what we call multi-track Turing machine. How do we specify the transition function of a multi-track Turing machine? Remember what such a multi-track Turing machine would do in a single step, that it will be in a certain state at a certain time. So, that is the present state. Okay. It will be reading 4 symbols in this particular example on the 4 tracks, because the read head is here. So, let us say it is reading sigma 1, sigma 2, sigma 3, sigma 4. These are the 4 symbols it is reading, and supposing the machine is in state Q. So, it is reading on the 4 tracks sigma 1, sigma 2, sigma 3 and sigma 4. Now, what would such a machine do? Its transition function must specify what will be the next state if on track 1 you are reading sigma 1, on track 2 you are reading the symbol sigma 2, on track 3 you are reading the symbol sigma 3, and on track 4 you are reading the symbols sigma 4. So, in such a case, maybe the next state is P and symbols written. It must specify. Maybe we will just say that sigma 1, this is changed to sigma prime, sigma 2 prime, sigma 3 prime, sigma 4 prime. Okay. So, it will obviously have the capability, it makes sense to say that it can simultaneously change all these 4 symbols. So, those are the 4 symbols changed, and then the move. So, this head which reads all the symbols in all 4 tracks simultaneously either will move one step to the left or one to the right. So, let us say it moves to the, in this case for example, let us say it moves to the right. Now, this is of course different from our basic model, because our basic model there was only one track, and so therefore, it could read only one symbol at a time. If you know, it is kind of obvious if you think like this, if you just see this, that suppose instead of thinking of all these 4 symbols being different, I mean different symbols, of course they may be different, but what I mean is thinking of this as a 4 tuple, instead of thinking of this thing as a 4 tuple, suppose I think of it as a single entity coding this 4 tuple. So, let us say what I mean is that supposing I have a code which will code or which will have a single symbol for all possible, I mean for every 4 tuple of symbols of the gamma, that is the tape alphabet of the multitrack machine. Imagine you are defining a gamma prime, which is basically you have a single symbol, single distinct symbol for every such 4 tuple, right. So, let's instead of 4, I can illustrate more simply the basic idea by just 2 tracks, and the point is not lost because you can just whatever I will do for 2, you can do it for 4. So, let us say you had and your tape alphabet gamma was just let us say 0 1, and of course, we have blank always, and that is the special symbol. So, supposing you had only 2 tracks, then on this what all symbols which can occur? So, you can have 0 0, 0 1, 1 0, 1 1, then you can have 0 blank, right, then you can have blank 0, right, then you can have blank blank and anything else. Obviously, you would also see 0 0 is taken care of, so that is fine. So, 2 blanks, and similarly you would have 1 and blank, supposing 1 1 which is there already. So, 1 blank, blank 1 and blank blank is taken care of. So, suppose you say you code this as A, right, this as A, this as B, this as C, this as D, this as E, this as F, this as G, and this is H, and this as I, right. So, now imagine if I had a tuple like for this 2 track machine Q, something like let us say 0 blank, P blank blank, Q. Conceptually, you can think of to represent this tuple as this 5 tuple quintuple as Q. For 0 blank, we had the symbol E, it goes to state P. For blank blank, we had the symbol G, right, and of course, I should say what is the move, right. Here I should say let us say move to the right. So, we move to the right. Now, this way therefore, just by changing the alphabet, see here originally the 2 track machine had 0 1 and blank, and here I have Q E P G R etc. Now, this is the quintuple corresponding to that, and so I have changed the alphabet set, input alphabet not input alphabet, the tape alphabet from 0 1 blank to this. Now, what is the new blank symbol, or what will be blank here? You may say G is the blank, because you would assume a blank means on blanks on both the tracks, right? So, G will act as the special symbol which will be there most of the places, and initially maybe the input is written on one track, other tracks are blank, which is fine, I can take care of this way. So, what I am saying is that a single step of a multi-track Turing machine like this can be taken care of by a basic Turing machine model machine by extending the alphabet set, right. So, here originally you had 0, 1 blank, and here we have A, B, C, D, E, F, G. Also we had something more, right, H and I. Right? So, your original alphabet for the multi-track machine had 3 symbols, and you have here so many other symbols, and that takes care of this. Therefore, it's now should be fairly simple to convince ourselves that if one could recognize a language by means of a multi-track Turing machine, by essentially changing the alphabet set, the tape alphabet set, I can do whatever the multi-track Turing machine was do by a basic Turing machine model. So, therefore, adding the capability of having multiple tracks on the tape does not really add to the recognition capability, in the sense what are the languages which can be recognized. That class of languages will not change just because from a single track you had multiple tracks. So, this is one possible generalization that one could think of, and we have found that it need not, or it will not change the definition of the class of languages recognized by Turing machine. So, now let us make a slightly more interesting generalization, and that generalization is that instead of one tape, whether single track or multi-track, that does not matter, because multi-track corresponds to, I can simulate by a single track, that I know. However, if we had more than one tape, then can we do something which with a single tape we can't do, right. So, what we are going to discuss now is multi-tape Turing machines. Multi-tape Turing machines. So, multi-tape Turing machines, let me make the simplest case for multi-tape Turing machine, that it has 2 tapes. But consider a Turing machine which has 2 tapes. There is, of course, we will assume that each tape is as before 2A infinite tape, and there is, of course, one as usual a finite control of the Turing machine, which basically means the Turing machine, this black box or whatever you call it, can stay in number of states, which is finite, of course. Now, so it is possible, since there are 2 tapes, this device must have the capability of reading from both the tapes and changing. So, therefore, we need to have, in this case, 2 read-write heads. One read-write head for tape 1, the other read-write head is for tape 2. So, imagine at some point of time this on tape 1, the cell which the tape 1 read head is reading is A, and let us say the tape 2 read write head is reading the symbol B. What happens? What is the transition, one step transition of such a Turing machine? So, again let us see what is the current scenario in this as we are seeing in this picture. Let us say the machine is in state Q. So, present state is Q, and symbol in tape 1 is A, symbol being read in is B. Now, you expect that the machine in state Q, depending on what symbols it sees in tape 1 and what is the symbol it sees in tape 2, it will make a decision about which is this next state it should go to. So, its corresponding move will be specified by saying what is the next state, which is, so let us say next state is P. Now, you have to also say what are the symbols that the machine would write in tape 1 and in tape 2, right. So, we say tape 1 symbol written, tape 2 symbol written. So, let us say it writes A prime here and writes B prime here or some other symbol. So, B is changed to B prime in this tape, A is changed to A prime in this state, and now the move. But you see that there are two heads, two read write heads, and obviously a single move will restrict. Supposing we just say left, then we would mean that both the heads must move to the left, or if we just say right, we may, do you want to restrict that both head 1 and head 2 move in the same direction? No, since we are talking of generalizing the capability of Turing machine, these moves can also be independent, in the sense one can move to the left, other can move to the right, or this can move to the right, this can move to the left, or both can move to the left, both can move to the right. So, we will say tape 1 head move and tape 2 head move, right. So, this may be tape 1 will move, head will move to the left, and tape 2 head will move to the right. So, you see a move of a 2 tape Turing machine, to describe it we need such a tuple, right. The present state, what are the symbols which the machine is reading on the 2 tapes, depending on these 3 pieces of information, the machine must say what is the next state it will go to, what are the 2 symbols it would write on the 2 tapes, and what are the directions in which the 2 heads will move, right. Now, it seems we have got an interesting generalization. Can we also, like we did for multitrack case, can we also take care of such generalization by means of our single tape Turing machine, right? So, again please be very careful in what is our objective. We have defined another way, in another way Turing machine, the Turing machine which has two tapes. Our question is that can there be a language which is recognized by such a machine which cannot be recognized by a single tape basic Turing machine model. So, that is the question we would like to answer. So, let me write the question clearly, that can a multi-tape Turing machine recognize a language which no single tape Turing machine can, can a multi-tape Turing machine recognize a language which no single tape Turing machine can recognize. If the answer is positive, to this question, then of course it means that we will have a bigger class of languages recognized by multi-tape Turing machines than the class of languages recognized by single tape Turing machine. What will prove, and again not too, the proof is not too difficult, the answer is no. So, again our single tape Turing machine is good enough. If we focus our attention to single tape Turing machine, that is good enough.